Wir haben den Soundcheck noch nicht gemacht. Wenn du den nicht machst, dann bin ich völlig verwirrt, dann kann ich nichts erzählen. Gut, hat funktioniert. Okay, good. Then I guess we can start. Okay, so we continue today with discrete Gaussian distributions. Just recall that we had these Gaussian distributions, and let me just go immediately to the multivariate stuff. This is the density function of the usual Gaussian distribution, where the density of an element decreases exponentially in the square of the distance to the center or the mean of this distribution. And in crypto, lattice-based crypto, we modify this slightly. We use this rho s comma c, where we put this pi in front. Basically, it's this pi here that goes here, and the 2 from here disappears. And then this is no longer a density function, but if we normalize it by 1 over s to the n, where s is the standard deviation, or people usually call it the parameter or width of the distribution, then we get this dsc. And this is the picture for it. And then we had all kinds of nice little things for it. I want to stress the concentration bound, where the probability of this distance to the mean decreases exponentially in the multiple that we are away in terms of multiple of the standard deviation. So even in the square. There are some constants involved that we don't need to worry about. And sometimes I use this alternative notation down there. So these were the continuous Gaussian distributions, the discrete based on lattices. We only look at the points on the lattice, and then we have to normalize using the overall weight of the lattice points, which is defined here. But other than that, that's it. This is discrete because lattice points are discrete. And one can show that all this here always converges. So this really is a number. And that makes, so the definition makes sense. Because we do this normalization anyway, in the original definition, it doesn't really matter whether we talk about d or rho. It disappears here anyway because of this normalization that's necessary here. So this is how we'll look at the Gaussian on the lattice. Okay, and then we also can look at these Gaussians on cosets, where instead of looking at points in the lattice, we look at points in the coset, normalized by the overall weight of the coset, obviously. And an important point here to notice is that we have that the weight of, or the density of v plus x, we can rewrite that as the density of x, but then move the mean. And then we also have that this rho s of v plus lambda of L is rho s of c minus v of L. Okay, so that's how we can also look at these things. I'll probably use that today. Simplifying, c is equal to 0, then we ignore it. S is equal to 1, we ignore it. And here I go again to this shifted, or the cosets actually that we can view as a Gaussian, as shifted Gaussian on lattices, namely this distribution here on dv plus L s. So I'll just take the mean here to be 0. If you want to include a mean, it doesn't really matter, include it. This is the same as, so here we take density or this distribution on v plus L. Here we take a distribution on L alone, but with the shifted mean, but then we add this v. So this here also gives us points in v plus L. Because here we pick from L and then we shift it, and here we take from the coset directly. And that's actually kind of neat. Okay. And this minus in here comes from the minus in the definition. And then the last time we looked at was a smoothing parameter, and the smoothing parameter of a lattice is a point or a number beyond which these Gaussian distributions behave nicely. In particular, they are concentrated like a Gaussian distribution up to this error term depending on epsilon. The smoothing parameter also depends on this epsilon. And there are many other things that I want to talk about today. And the important thing that we also have is that we have this bound on the smoothing parameter. For epsilon larger than 0, we know that the smoothing parameter and eta epsilon is bounded by the length of the Gram-Schmidt normalization of any basis for the lattice times this factor here that is roughly ln n divided by epsilon. Right? So this plus here is just to cover the case that epsilon is larger than 1. But roughly this is ln n divided by epsilon. And if you look at it more closely, then we can argue that for any function in omega square root of log n, so that grows faster, asymptotically faster than square root of log n, there's a negligible function epsilon of n for which this eta epsilon of n of L is bounded by b tilde times this omega square root log n. Okay? So if you go slightly above the length of this basis length, or the Gram-Schmidt version, by this term here, then you are beyond then you already are beyond this smoothing parameter for a negligible epsilon. Okay? So, and that's how we usually work with this. We take this thing here for some specific function, and then we know that we are above the smoothing parameter for some negligible epsilon. What that negligible epsilon is, if we talk about asymptotic security, that doesn't really matter. If you want to have concrete values, look at this formula. Then you work with that. And there are other bounds known, but this is probably the one, at least this is one that I work with today. And then we looked at the Gram-Schmidt orthogonalization, but I won't repeat that. Here's a picture for it again. So now, what are the interesting properties of the smoothing parameter? So the first property says that when we have have an S that's beyond this, larger than the smoothing parameter for an epsilon between 0 and 1, and for an arbitrary mean, we have that the density of L, S comma C, is almost the same as if we take here the mean 0, up to this little term here, 1 minus epsilon divided by 1 plus epsilon. Okay? Which means that the overall weight doesn't really matter, or doesn't really depend much on the C. Which also means that, which I said at the beginning, we blur the discrete structure, because we can move this thing around, the Gaussian, but it always gives us roughly the same overall weight for the lattice points. So it's kind of almost independent from this C. Okay. So, and you can hear 1 minus epsilon divided by 1 plus epsilon. 1 plus epsilon is roughly 1 minus epsilon. 1 over 1 plus epsilon is roughly 1 minus epsilon. So this is 1 minus epsilon squared. So if you take, for example, epsilon to be 1/3, you get 2/3 divided by, what is it, 4/3, and then you get some nice value, 1/2, to be precise, right? But if you move epsilon to be 0, I mean, this becomes almost 1. Yeah, so it's almost the same. So these things. Another thing that we have is that now we are really talking about here. I talked about this rho, but now I talk really about probabilities. That's why I go to D as comma C. And we have our letters and C as before. Now we just need that epsilon is larger than 0, but S needs to be at least twice the smoothing parameter for epsilon. And then for any x in L, the probability, if you pick something in lattice point according to this distribution here, the probability of getting x is roughly 2 to the minus n. Up to this point, up to this factor, and this time it's 1 plus epsilon divided by 1 minus epsilon. We want an upper bound, so this better be larger than 1. Okay? Well, if it was smaller than 1, would be even better, but here we have to give it a little bit more slack. So it's roughly 2 to the minus n. Okay? So no lattice point has significant probability given this, this distribution, if the smoothing parameter is if S is large enough. Okay? And you should think about this in particular if C is 0. Okay? Then the most likely lattice point is the origin. If it's 0, then the most likely lattice point, because of the definition of our distribution, of our density function of a distribution, the most likely lattice point is 0, but even that has probability at most 2 to the minus n. Okay? In particular, this also implies, of course, that if you pick 2 points according to this distribution, the probability of picking the same point twice is 2 to the minus n, roughly. You don't have a very large collision probability in this sense. So this is also a nice, and I'll use this fact actually today in one of the proofs. Now is another thing that tells you that these Gaussian distributions, or the discrete Gaussian distribution, behave very similar to the continuous Gaussian distributions. Namely, again, we pick a point according to this distribution, DLS, C. And then we are interested in what's the probability of picking a point that's far away from this guy here. Far away, S times square root of n in this case. And the probability for that to happen is, again, roughly, is upper bounded by 2 to the minus n. Okay? So why is that? So if we go back and look at the continuous case, and look at this here, and if we pick here lambda to be square root of n, we get here something e to the minus a times n. So almost exactly up to this a, which is, you can choose it anyway. Well, I could even give you a number, but never mind. Okay? So here, in that respect, they behave very similar. The Gaussian distribution will pick points that are far away from the mean with very small probability. The same is true for the discrete Gaussian distribution, but you always have to do that with respect to multiples of the standard deviation or the width. So, and the square root of n, it's kind of a normalization. Okay, so this is the next thing about this nice Gaussian distributions. Oops, here's another fact. So let L and L prime be n-dimensional lattices, with L prime being a sublattice of L. So it's a lattice itself, but it's a subset of L. And then for any epsilon now between 0 and 1/2, and any s larger than the smoothing parameter of lambda of L prime and every c, the distribution of, I pick a point from the lattice according to this distribution, And then I do a mod L prime. Okay, so I take the division with remainder, but these are all additive subgroups, so there's mod. Okay? Okay, and this here is a subgroup of this here, so you take the quotient, the quotient group. Okay? And then this distribution is almost the uniform distribution over this quotient group. Okay? So, but you pick, so the point is here, this S depends on the smoothing parameter of L prime, but you pick that here. Okay? The reason for that is that the smoothing parameter of this L prime will be larger than this of L. It's sort of sparser, and hence it's sort of more difficult to get the smoothing. But then we get something that's almost uniform in that setting. And that turns out to be very useful in several applications as well. Okay, and finally, we have the following thing here, and let me, to do that, let me look at lambda L. Assume that that is z to the n. Okay? A basis for this here consists of the unit vectors. And obviously, in this case, the Gram-Schmidt version of B is B itself. And hence, we have B tilde is 1. And then we know that for all epsilon, the smoothing parameter of Z to the n, which is the lattice, so it has a smoothing parameter. This is lower bounded by, so we can use again our bound from before, the general bound that we had here. It's less than this B tilde is 1, so we just have to take this ln 2n1 plus 1 over epsilon divided by pi, and we take the square root. Right? And if we want something for a negligible epsilon of n, again, this disappears. So it suffices to take any function that grows larger, faster than square root of log n. Okay? Okay. So then we take a discrete Gaussian distribution on Zn. And it's enough to take this value here, this guy here, and then we'll have all these nice results. Okay? So, and here we say that this is sometimes or often called regularity. So it says that we are looking at, for a matrix A and ZQn times n, we look at A times E, where E is distributed according to this discrete Gaussian distribution on Z to the m, with an S that is larger than the smoothing parameter of Z to the m. Okay, so that's why. So this here means S is larger than the smoothing parameter of Z to the m. And this thing here, if I take that mod Q, this U that I get, so I get this induces, by picking this E according to this distribution and doing this here, this induces a distribution on that Q to the n, because I have A from this set here. And what this says is that for appropriate parameters, this is statistically close to uniform. So it's the distance to the uniform distribution is negligible. The parameters that we have is that m must be larger than 5n log q. Okay. And this is true for almost all a. So you can even fix a. So this is not true. This doesn't depend on a being chosen by any way, except there is a small fraction of a's for which this is not true. The reason that we have to exclude a small fraction here is pretty obvious. If this guy here doesn't have rank n, okay, then by doing this product here, no matter what we put in here, we cannot write everything as an a times x. Yeah? And then you cannot hope that this is, well, actually you will exclude complete subspaces, which means you will not be able to be close to uniform. So often how you can rephrase this is actually, so if the columns of A generate all of zq to the n, then this is true. Okay? And we can show that at most this fraction of a's in zq to the n does not have the property that its columns generate all of zq to the n. And for that, we also need that this is large enough. Okay? Well, not just for that, but among other things, we need it for that. Okay? So that's why, so this is basically, we have to exclude some things. Otherwise, this cannot be true. But then this is close to uniform. Okay? And we will see that is an important property for the pre-image sampleable functions that we already defined last time. Okay. Okay. Now, these are all the things that I mentioned so far are all properties, mathematical properties of these distributions. But we want to use these distributions in cryptographic constructions, which means that we somehow should be able to pick points according to this distribution, or at least something that's close to this distribution. Okay? And it's usually good enough to sample statistically close to a distribution. You should always prove that for yourself, like once per 3 months or so. If I have something that's true for some distribution, and I have another distribution that's statistically close, then it's also true for the statistically closed distribution. Okay, and here is the first thing. So, and we want to do that using our trapdoors for lattices. And we had 2 different types of trapdoors, or the one was short basis, and the other was a gadget-based trapdoors. Okay, and also from which distributions we can sample efficiently depends on the quality of the trapdoor. And they are directly related to the S. So the quality of the trapdoor that we have determines for which S we can sample efficiently and statistically close. And the first one says that, our first theorem says that there is a probabilistic polynomial time algorithm that given a basis B of an n-dimensional lattice and a parameter that's, again, so this S should be larger than this, which we know is larger than the smoothing parameter. And it means C outputs a sample from the distribution that's statistically close to this guy here, to the distribution DLS, C. Okay? So now, why did I say that the quality of the basis determines from which kind of distributions we can sample? This is always just an upper bound for the smoothing parameter. And that's true for every basis. But if we have a nice basis, then this here will be short. And we can do that for much better S, for more S's. Okay? If the basis is bad, then you can always only sample from this, period. And if you have a basis and I have a much better one, then I can sample for smaller S's. And if you go back, sampling from smaller S's, for example, means with high probability, you will sample shorter vectors. So there is a direct relation between these things. So sort of this means that if I have a nice basis, I cannot just compute short vectors, I can even sample short vectors. And how short they are depends on the quality of the basis. Good, and obviously this is a probabilistic algorithm. I mean, there's something about with the distribution, right? So it better be probabilistic. Okay, this is again, statistically close, you can make that more precise. I could replace this here by this term, and then this is, well, it's close up to some factor that again depends on epsilon. But for this, if I pick this here, then I know that this epsilon is a function in n that's negligible, and hence that's what I mean by it's statistically close. It differs from it by a term that's negligible in n, in the lattice dimension, and nothing else. Okay. So that's the point for the case where we have a basis, a short basis. This is often good enough, but for many applications, we rather work with our gadget trapdoors. Okay? And I will give you also a statement that given a gadget trapdoor, you can also sample from these distributions. And this actually take the detour via this theorem. You can do it directly where you get a slightly better parameters, but not much. Okay? So, and okay. It's, as I said, if we go back to this generalizes to sampling on cosets of lattices. Why? If you go all the way back to here. Sampling on cosets of lattices, sample on the lattice, shift. But here it's important that we not just be able to sample from with mean 0, but with arbitrary mean, because that is what we want here. Now, we go, this is this, now we want, and if we, now if we transform that, how good a basis can we compute? Sort of. This just said this is true for everything, for every lattice. Okay? Now we would like to see what can we do when we actually generate our lattice together with a trapdoor, which is a short basis. And this says that when we sample A with a short basis, as in theorem 3.1, there we saw that we can actually sample or get a matrix together with a short basis, where the matrix is close to uniform on this set of all matrices that we consider. Then we can get a basis that has length roughly m to the 1/2 plus epsilon for any epsilon positive. And then we get this basis S that has this length, and then the parameter, previously it was S, now it's R, from which we can sample is really this type here, and then we can sample from this here, and which is the lattice from which we'll sample is lambda perpendicular of A. So all points that get mapped to 0 using A. Okay? And this is the combination of theorem 3.1, which says we can sample A together with a short basis that has length this here, and then do that with the other theorem, with the previous theorem, and then you get this. Yeah? And here I directly included that we can do that for cosets or for arbitrary things. Yeah? Let me just tell you, so is that the right thing? Yes, good. Yeah. Okay. So now what can we say about gadget trapdoors, which we know how to do for these things as well, for these lattices. Remember, the gadget trapdoors were these gadgets where we use this gadget matrix A, and then we hide this gadget matrix. So this was, we basically had this A was generated as an A bar, concatenated A bar H times G minus A bar times R, right? Where this was our gadget, and the trapdoor in that case was simply this, or that takes a bar, which is R. Right? The reason for it is that we had this as A times R, is simply H times G, and this H was something invertible that doesn't really matter, but using that relation, we were able to transform everything that we get here to something we get here, or in this A, using that thing here, this R. And for G, we had all kinds of nice results. And in fact, one of the results that I didn't mention there is that when we have this gadget matrix G, then this lattice lambda perp of G has a basis with length at most 3, where the Gram-Schmidt version has length at most 3. In fact, it's square root of 5. Okay, and it's an explicit formula for this S. Quite simple. So with this G, we can directly output this S as well. Okay, so which means that since this is short, we can sample from lambda perp, distributions on lambda perp, discrete Gaussian distributions on lambda perp. And the factor in there, if you go back here, this here becomes 3. So it's subsumed basically by this term here. Okay. So the question is, can we transfer that? Can we also get, given a short basis for lambda perp of G, can we also get a short basis for lambda perp of A? Okay. And that should depend on this guy here. And in fact, it does so in a very nice way. Here I use this R as a trapdoor. As I told you, you can view this as R as a trapdoor for this G, or this R bar as a trapdoor. And if I have, and this H was called the tag, and so if I have an R bar be a trapdoor with tag H for A, then we can compute a basis for this lattice here, that whose length, or the Gram-Schmidt version of it, has a length that is the Gram-Schmidt version of S multiplied by this term S1 of R bar plus 1. S1, remember, is the largest singular value, the one where it stretches most. You can imagine that this sort of plays a role here because it stretches the basis. Okay? The +1 base comes from this identity here. You have to include that. Okay? So we do have good bases for G and also for H times G. That doesn't really matter. And if we have a nice trapdoor, namely one where this guy here is small, then we also get a nice basis for A. On top of it, as before, we want to be able to do that for most A's. Because like in the theorem that we had here, this is except for a negligible fraction of all A, for almost all, or what this theorem 3.1 does, it samples A almost according to the uniform distribution. It's almost a uniform distribution. Why is that important? Well, A will probably at some point be a public key. And public keys should always be sampled according to some nice distributions. Otherwise, they don't have enough randomness in there or not enough entropy. That's bad. Okay, so what we want to be able to prove is that for most A's or so, we can get a nice R bar. Or if we choose nice R bars, the way we generate these things, obviously, we pick R bar, and then this is our new A for some H that is fixed. Okay? And this is what the next theorem tells us. First of all, if R bar is chosen with deviation S, which means that every single entry of R is chosen according to the distribution on Z, the discrete Gaussian distribution on Z, with this parameter here, which should by now be familiar to you. Get used to it. It shows up everywhere. And I try to explain why this is natural. E to the minus x squared, right? X squared, the square root, e to the log verbs. Okay. Then, with probability negligibly close to 1, we have that S1 is roughly order S square root of m. Okay. Typically, it doesn't really matter whether I put in here an n or an m because they are related by some small factor. So if we choose this, then this is small. So we get here something where, well, the length is, well, it depends on this s here and the square root. So we get roughly here it's 3. So we get 3 times square root of m times the square root of log. Okay. But how many of these A's can we generate with that, right? Or what is the distribution on the A's? So if we have a distribution on the R bars, then using this formula for fixed H, we get a distribution on these A's. It's always an induced. And what is the distribution? And this is the way we go for it. So if we sample A with trapdoor R bar using this parameter as in the previous theorem, then there exists a polynomial time algorithm that, except for a negligible fraction of all A, on input A trapdoor R bar and a parameter R, outputs a sample from the distribution that's negligibly close to this thing again. Okay? And this R here is square root of m omega of log n. Okay? And this is not a typo, although for a second I even thought a second ago that it's a typo, but it's not. Why it's not? Because we get a square root log m or n from this here. We need to sample, we get this here. Yeah? But we also get one from here, another square root log m factor. And hence, we get a log m factor. Good, so it's not a typo. And it's still better than this one in many asymptotically, because here we have an epsilon larger than 0. So here's square root of epsilon, square root of m plus m to the epsilon, and then here's the square root of log n. In this version here, we get rid of the plus epsilon and pay a square root log m factor. But as you all know, m to the epsilon is always growing asymptotically faster than square root of log n. So this is slightly better asymptotically. Yeah. As I said, you can do it directly, then you get better constants. But never mind. So you won't notice it here. Okay? So with both types of trapdoors, small bases, and the gadget-based trapdoors, we can generate A's together with trapdoors such that we can sample from these distributions almost exactly. And the parameters are slightly different, but the important point is it's always including the square root of m. Yeah? So for these types of lattices, we can roughly sample with parameter square root of m. Yeah. Okay. Yeah, this is what I said. It's really somewhat better. If you really go into concrete schemes, you probably should look at the other paper. But it's not so easy to digest. Why it's better, or where the improvement comes from. Okay. Okay. So that's it for this part here. So we can sample in particular from these distributions on these lambda perp lattices with probability with roughly a square root of m. And remember, that's important to keep in mind. We had an upper bound on the length of the shortest vector in these lattices that used the pigeonhole principle. Okay? And that gave us a bound that the lambda 1, the length of the shortest lattice vector in here, is at most square root of m. Yeah? Because for these m's there where we have is larger than n times log q, we looked at 0, 1 to the m. It's larger than zq of n. So there must be two vectors, 0, 1 vectors that get mapped by a to the same vector. So they lead to something that's, the difference of them leads to something that's in here. And the length of those things is square root of m. Huh? And that bound is not far from the truth. Okay? So we can sample things that are pretty close to shortest vectors. Okay? Slightly farther away. Okay? Slightly longer, which probably is just necessary because you want to have lots of them. Okay? You want a distribution that's not concentrated on just a few of them. Okay? But you want lots of them. So this is close to best possible using these kinds of arguments. Okay? So you should also square root of m as well, roughly the lambda 1 of these lattices, so we can sample roughly with the length of these things. We have to spend a little more. Okay, but you need these trapdoors. Yes. Okay, good. But these are not the only things that we need Gaussian distributions for. We also need them for the LWE distributions. Remember LWE, we had this, I don't know, let's do it this way. A transpose times E plus S times E. And we were arguing that given the right parameters and this here chosen according to some distribution, then this here is indistinguishable from uniform. Or even if I give you this here, where A is now uniform. But this second part here, you cannot notice it, that it comes from A transpose. Yeah? Where this E produced things that are pretty short. Okay? We wanted these things to be short. Clearly, if you do that with a uniform distribution, the statement is obvious, right? Then you can just view this as a constant. And then you add a constant to something uniform that's still uniform because it's a group. And so the interesting thing is that this is true for short E's. But so what is the kind of chi? This is a Greek letter. It's pronounced chi. So what are the distributions that we hear? And in particular, what are the distributions for which we can prove this hardness result or this indistinguishability result? And I just want to briefly mention how you define that. There are basically two equivalent ways of doing that. The first one is probably the easiest one. You choose, or actually this E is chosen from chi to the M. So M times M entries using the same distribution. And the easiest way is you just take the discrete Gaussian distribution on Z with this parameter here. Square root of 2 times alpha times Q. And we had this funny, we talked about this before, but what we need is that alpha times Q must be larger than 2 times square root of n. Okay, that was this alpha Q. Okay, something like this. Okay, so this is roughly square root of n. Okay. This is already a discrete distribution. So it's Z. In fact, what we usually do is we take this to be Z this thing modulo Q. We take this as a distribution on Z, and then we reduce modulo Q. Pick it from this to modulo Q. And if you do that, you actually get something like this. So here, what you do is modulo Q, you should always think of mod Q things as a circle, right? Because it goes round and round and round and round, right? Q plus 1, you go back to 1. Q is 0, okay? And what you get here is, this is the Gaussian distribution that on these things that you get from ZQ if you do that. So most of the stuff is here would be 0. It's a range on the circle. Here is 0, which clearly has the highest density or probability. And then it drops off as you go further away. And you always use this centered representation. So the set of representatives, namely minus Q half to Q half. Yeah. Okay, and then with that idea in mind, you know that the smallest one is sort of Q half or something. Okay. And this here simply means that alpha is smaller, alpha is larger. You take alpha to be larger, you dampen it a little bit. No? It's not as much concentrated. Just to prepare you for things that you may see in the papers, the original definition of Regev that he used in this reduction of LWE to distinguishing LWE to SVP and SIVP was different. And the first thing that you do is you look at R modulo Z. This is the unit interval, but again, you glue it together. Yeah? It's like a circle. Yeah? Okay, and then what you do is you can define a distribution on this T by picking an element from the normal distribution with mean 0 and this as standard deviation. Do that mod 1. Mod 1 means ignore the integer part. Now that's mod 1. This gives you first a distribution on this T. Okay? And then what you do, from that, you can discretize it again to get something on ZQ. And to do that, you can pick an arbitrary distribution on phi and a Q in Z, and then you get a distribution on ZQ by you pick an element according to this phi. Okay. Then you multiply it by Q, round it to the nearest integer, and take that mod Q. Okay. What does this mean? Basically, this phi times Q. If you look at it, so here we have this phi. And phi times Q is always less than Q. Well, it's not less than Q, but it's some integer. Well, the way I did it is less than 1. Okay? Okay? And then with this thing here and mod Q, you partition this unit interval into, what am I doing? No, yeah, phi times Q. It's less than Q. Because phi is less than 1, at most 1. Okay? And by doing this here, you partition this thing in intervals. Right? For each one, you have 1, but the intervals, they grow larger and larger. Okay? Because this thing is concentrated. And if you end up in here, output 0. If you end up here, 1, and so on. That's the way you can view these things. Okay? Actually, the way I wrote it down, you could actually take here R itself, the distribution on R, not necessarily T. Not that it matters much. And then, in some sense, you can prove that if you want to discrete, this is basically the same as this. There's a small difference between the two things, but it's not really important. Okay? I find it always more convenient to just view it as this here. Okay. But technically, this is the one that, if you want to do reductions, which you probably never want to do, leave that stuff to Regev and Picard and stuff. You need to use this here. Okay, good. So these are our Gaussians on lattices, in particular Gaussians on integers. Okay. Now we want to use all this stuff to construct collision-resistant functions, to construct secure signature schemes, and to construct CPA-secure encryption schemes. That, because we think that all this stuff is post-quantum secure, the lattice-based stuff is post-quantum secure, these things lead to post-quantum secure constructions. Okay? And signatures I'll do today, encryption schemes I'll do next week. The signature schemes will be based on SIS, the hardness of SIS. The encryption schemes will be based on LWE. Yeah. Good? Good. Okay. Let's do it. Then we should go to this. And now we want lattice-based cryptographic constructions. And a couple of weeks ago, I told you about pre-image sampleable functions as an important ingredient, or it's a nice abstraction to obtain signature schemes, hash-based signature, or using random oracle models. And that is a generalization from full domain hash RSA. Okay, and here is and first I'll show you how to construct pre-image sampleable function families using lattices, and then I directly apply that to get signature schemes and do that proof directly. Okay. So what was a pre-image function family is pre-image sampleable if the following condition holds. First of all, we must be able to sample keys. Function families are always families of keyed functions. And we must be able to sample keys with trapdoors TDK according to some distribution determined by a security parameter. And usually we assume that from TDK one can efficiently determine K, although later on I will actually write this down explicitly. So that's the first thing. So we can sample according to some distribution from the function family. Furthermore, there exists an efficient probabilistic algorithm F-1 or F inverse that gets as input pairs consisting of a trapdoor and an element Y in YK. Okay, it's just an algorithm so far. The important properties come now. Okay? For each key, there exists an efficiently samplable distribution dk on xk. Fk goes from xk to yk. Xk is the domain of Fk, Yk is a range of Fk. So there is an efficiently sampleable distribution on Xk such that the following distributions on pairs from Xk, Yk, so pairs from one element from the domain, the other from the range, are indistinguishable. The first one is I pick X according to this distribution and let Y be Fk of X. The reverse direction is I sample Y from Yk, and since I don't put in here a distribution, just a set, this means choosing it uniformly at random from the set. And then I apply F inverse. And that gives me an X. And these two distributions, the first one is determined by X and this distribution here, which is in most constructions not the uniform distribution, but something else. And then I get this Y, but Fk could, this is a function. So this element is determined by this element. And the second distribution is I start with a random image, and then I sample a pre-image according to the algorithm F inverse. And this algorithm is a probabilistic algorithm. Okay? So even given Y, this is still a distribution. Okay? That's important because I never said that the fk's or f is injective. Okay, so here I will, for many x's, I may get the same y. Okay, so this guy here, if it gets a y, it's still, the image should not depend on y alone, right? Okay, it must have some independent randomness, independent from the random choice of y. And that randomness comes from f inverse. Okay, now we can construct such a thing, namely a lattice-based PSF. And the security parameter is 1 to the n, and our sampling algorithm, the sampling for keys together with trapdoors, is simply sample matrices A together with a basis T of length m to the 1/2 plus epsilon. That's it. So that's the key generator. You could also do that with gadget trapdoors. Never mind. Okay? This is just one way of doing it. And then I set L to be m 1/2 plus epsilon, S to be L times omega of log n, just to avoid writing all these 1/2 plus epsilon stuff. Okay? Then, as I said, A is a key and T is a trapdoor TDK. Okay? In this case, the domain of a function with public key A depends only on n, not on the particular choice of that key. That's why I also call xk to be dn. So it just depends on the security parameter n. And I take that to be all e's in z to the m that are bounded, whose length is bounded by s times square root of m. Yeah. Yeah, that's okay. Yeah. Okay, so, and yk is also only depends on n, and zq to the n. So the domain and range depend only on n, not on the particular key, which is. And the distribution on dn is a discrete Gaussian distribution on z to the m with deviation width parameter, whatever you like, s. And I should put in here L, I think. No, I should put in m to the plus epsilon. Never mind. No, it's okay. Okay, it's okay. No, it's correct. Yeah. I take this at m. Okay? Good. And as I explained to you, from this basis, from this distribution, we can sample using the standard basis consisting of the unit vectors. Right? Because this is, there we saw that we just need this here. Right? But I even give you this. So the sampling is no problem. Okay. And now we need to show that we have the other properties. Namely, we have, in particular, 0.3. And so now what is the inverse algorithm that we do? On input A and T and S and U. U is the image for which we want to sample from the pre-images. What we do is we compute a T, little t, satisfying A times T is equal to U. Arbitrary. Okay, I don't care. And then I sample V according to this distribution, AS from minus T, using the trapdoor T. Okay. Okay. Recall that this distribution here, D, I should have put here lambda perp of A. This should be lambda perp of A, sorry. So, and we know that d lambda perp of a comma s comma minus t is the same as t plus d lambda perp of a comma s. Now what this thing here does is, and we output t is e to be t plus v. Okay. Okay. So first of all, did I put this on the slide? I don't think so. Yeah. So now I need to show you that this leads to something that's short, right? That is according to this that is short, and that it's, and then I also want to prove that it's collision resistant. Okay. Now, if you look at this here, let's look at A of E, which is A of t plus A of v, right? This I know is u, and this because I pick according to I pick from this thing here. This is 0. I pick from this lattice. Now would I? Yeah. Okay. So this is u. So at least this satisfies what I want. This is picked from the uniform distribution. Is it short? Yes, it is short because what I do is I pick my E in such a way that E minus minus t is short. Right? With high probability. This is minus minus. This is in U center, but it's minus t. So this is also short. And in fact, with high probability, E is of length at most s times square root of m. Where I use my lemmas, that if I go square root n or square root m in this time square root dimension above s, then this happens, that this is not larger, happens with probability 2 to the minus m. Ignore it, doesn't happen. Okay? And that this is short is really, and yeah. Yeah, this is because of this construction here. This is, yeah. Okay. Now, in the proof, so the ingredients to prove this, what are the ingredients? First of all, obviously we need theorem 3.1 to generate keys and trapdoors. Then we also need lemma 4.a for correctness, namely that what does lemma 4.8 say? Let's go to it. It says that this is that if we sample according to this distribution, we get something outside this with small probability. So when I look at this here, the inversion algorithm here, if I pick this something from dn, if I pick it according to this distribution, that happens with small probability that it's outside. Okay? I can use the sampling algorithm to do that. Sample from not exactly this set, but with high probability from that set. If it's outside the set, just throw it away. Resample. Nice exercise. This is statistically close to the distribution you want. And then we also need Theorem 4.12, we always need to sample from these things, these distributions. That's something that we saw in 4.12. And then we had lemma 4.10. This is our regularity lemma here that these distribution matches. If I take something from this distribution and A times E, then I get something that's statistically close to uniform. And that is the distribution on the range. Okay. And the collision resistance is actually the easy part. Right? Well, if you give me two images with the same U, well, you have S, A times S is equal to A times S prime is U. Well, then A S minus S prime is 0. And if S and S prime are in here, then the difference is in the set where I put a 2 in front of it. Actually, the square root of 2. So that's why I have this 2 in front of here. So if I find a collision, I can do this. So if this is hard, I cannot find collisions. Okay. So you can see that already a lot of nice things go into this construction and into this proof. Oh. Oh. And now we want to even prove a lattice-based signature scheme. In fact, you can do a lattice-based signature scheme given a PSF and a random oracle. I will do it for this lattice-based stuff. I will do, the proof is almost the same. There's just one more ingredient that you have to put in. So to get my lattice-based signature in the random oracle model, let F be the lattice-based PSF described above. The key generation of the signature algorithm uses the key sampling algorithm for F to generate A with a trapdoor T. We set the public key to be A, the secret key is A, T. Just for convenience, I include A. Doesn't really matter. And I also have a function H from 0, 1 star to ZQN that is modeled as a random oracle. Formally, syntactically, it's arbitrary, but later on I'll use it to find a random oracle. Now, to sign a message using the secret key S, I use my inversion algorithm to find a sigma in Dn such that A times sigma is H of M. So H of M is the image of M under my random oracle. Well, find a pre-image for this random string. Okay. And I output sigma. And the verification does two things. First, it checks that sigma is in Dn, so it's short, at most S times square root of M. And second, it checks this equality. And that's it. This is like full domain hash RSA. And it's actually the blueprint that I presented to you a couple of weeks ago. And the point is that assuming again that SIS with these parameters is hard, then the above scheme is strongly existentially unforgeable under adaptive chosen message attacks. So it's even strongly unforgeable. You cannot even take a message signature pair and compute a new signature, given all the other things that you have. And so first of all, the scheme is correct. Okay, follows from the previous argument. It's a PSF, which we already saw. It's correct. Sometimes you have to recompute, but again, it doesn't really matter. Or say the algorithm fails with exponentially small probability. Doesn't really matter. But anyway, it's a nice exercise. I have an algorithm that rejects with a small probability. I do that until I have success that this is statistically close to the true distribution. Something like this. Never mind. Actually, so how do we prove this theorem? Where's my... This is all we got, yes. Okay, so obviously we do a reduction proof. That's proof. And we do a reduction. So A is an adversary winning strong S I E U F existential unforgery and the chosen message attacks game against scheme. Okay, strongly existential, unforgeable, and the chosen message attacks. And now we construct S against SIS with the parameters n, q, 2s square root of m. And what we do is we just run A. S just runs A. S simulates A. Okay. But then, if it simulates A, it has to answer the hash queries and it has to answer the signature queries of A. We are in the random oracle model, so we also have the freedom to answer our hash queries. That's the important point here. That's the advantage of this random oracle model. We can, as we sometimes say, we can program it. So a few things that we assume for A is A, these are all without loss of generality. Before signature query on message M, A queries H on M. Okay? So whenever it makes a signature query, it has previously queried the random oracle. If that's not true, then actually the signing algorithm will query the random oracle. And then doing it before that actually gives A more information. So we can always transform an A that does not do it into one that does it, and that gets more information, so it's better. And secondly, if A outputs M star, sigma star as forgery, A has queried H on M star. Okay? Again, if it did not do that, it doesn't even know for which value it should produce a pre-image. And can you easily argue that in that case, its success probability is 2 to the minus n at most. So doing it can also just modify the success probability by something that's negligible. So these are the two things that we need. So how do we, for every signature query, what S does is so as follows for every hash query, what we do is we pick a sigma on M in 0, 1 star. Okay? We pick a sigma M according to our distribution dn, which is this dA whatever, right? With our sampling algorithm. Yeah? And then we set h of m to be A times sigma m mod q. This is our value. Okay? And we store m comma sigma m in a table. Okay, T. Let's call it T. Yeah? Remember that we already answered this part. Okay? And then for every signature query on M, okay, look up table, look up T for pair M comma sigma M. We assume that A has ants queried before and return output sigma M. Okay. Yeah. Now, so what I do here is to answer the queries, I reverse the direction from the signature algorithm. Instead of going the reverse direction, namely I have h of m and then I invert, I pick it from the right distribution and then go the forward direction. Right? So this is, in one case, I do in the signing case, in the real case, I would use the reverse direction for signing. Here I use the forward direction. But as we know, the two distributions are indistinguishable. So this thing here that I'm cheating here doesn't the adversary doesn't notice it, except for negligible things. Huh? Good. Now assume when A outputs a forgery M star sigma M star, what we do is look up table T for pair M star sigma star. And here I look at M sigma star. So he produces some output, which is M star sigma star. But I assume that he has queried H on M star before that. And he obtained this H of M as A times sigma M star. And so there is a sigma M star in my table for this M star as well. Output sigma star minus sigma M star. I hope that the two are different. We hope that the two are different. Yeah. Okay. Okay. So because the view of A here is almost as in the real game, it produces here a valid forgery with some probability epsilon. So A success probability is, say, epsilon, which is an epsilon of n, and then simulated A produces valid forgery with probability roughly epsilon. Again, slightly different because the view is not exact as in the real game, but close enough. Yeah. Now I want to argue that I can transfer that into a solution to SIS. Yeah. Okay. Now there are two cases. The first one is that we have a made a signing query on M star. Okay, so it tries to find a new signature on a queried message and received, well, in that case, it received sigma M star. But if A is forgery valid, then sigma star is not equal to sigma M star. Okay? Oh, which implies then A times sigma star minus sigma M star is equal to 0 mod Q. But this is not equal to 0. And again, it's the length is as we want it, because both are from the right set. Okay. So now the second case is A made no signature query to M star. But it did make this query, this hash query. Yeah? And I need this here. But A, so A made hash query, which implies that M star, sigma M star is in T. But A received only U, which is H of M. Okay? That's the only thing. Yeah? So the view that A gets is statistically independent from this guy here, up to this U. Okay? Okay? Hence, it produces some. So then the question is, what's the probability that sigma star is equal to sigma M star? Okay? Okay? But its view is independent, basically, of the sigma M star, except for this guy here, for this U. But now, we take one of our nice little lemmas, namely this guy here, 4, 7. he outputs something, and since it's statistically independent except from this value u, I can imagine that now I pick the sigma m star after he has picked this sigma star. And then the probability that I output the same thing again is just 1 to 2 to the minus n. Okay? Lemma 4.7. So in that case, we win with probability roughly epsilon minus 2 to the minus n. S wins with probability epsilon minus 2 to the minus n. Which implies that we know that this must be negligible, hence epsilon must be negligible. And we are done because of our assumption. Yeah. So here is we need this to be, we have many signatures for every message we have many signatures. But we don't reveal these things, and hence we get this theorem. So this is then this theorem. And I guess that's it for today. Next time we talk about encryption, LWE. Same time, same place. Unless there are questions, of course. Yeah. Just one more thing just to mention, because we have this lemma 4.7 and we know that this function here, a times this is collision resistant, one can actually easily deduce it from it that the function is one way. It's a one-way function. Basically, I just proved it. Oh, well, actually, it's easier because. Yep. Okay, no questions? Good. Then we continue next time with LWE. Thank you.